Welcome everybody to today's webinar, Implementing Secure Software Upgrades in Embedded Systems, Best Practices and TPM Integration. We're thrilled to have you here with us as we dive deep into one of the most critical aspects of embedded systems security, ensuring its integrity and the security of software upgrades. Before we begin, let's go over some quick housekeeping items to ensure a smooth experience through today's webinar. We will have a live Q&A session at the end of the presentation, so I do encourage you to submit your questions and we will be answering them at the end. Feel free to type them in as they arise, and should you encounter any technical issues or need any assistance, just send a message through the chat and our webinar admin team are here and we're ready to help you. So, who is FIDOS? Well, we were founded in 2001 and we have since grown into a 150-person, all North American embedded system services company. We serve all industries and markets and have 3 brick-and-mortar locations in North America, 2 in Canada and a US home base in the Silicon Valley. We've been working with embedded systems since 2002 and we're the proudest of our repeat customer rate. Close to 95% of our customers return year over year with new projects and new business. A real testament to the quality and efficiency of our work and our commitment to doing it right the first time. We have an exceptionally strong partner ecosystem with strong partnerships with AMD, Altera, formerly Intel, Analog Devices, and Lattice, to name a few. Most recently, this past July, we were thrilled to have been announced Partner of the Year by AMD. In our first decade, FIDOS did a ton of varied AMD Xilinx-related work. And so in 2011, Xilinx asked FIDOS to become their first ever Premier Design Services member in North America. To this date, we have collaborated closely on opportunities and trained together on the latest technologies, such as Versal and their latest Embedded Plus architectural series, all with the end goal of helping our joint clients get their solutions to market as accurately, quickly, and smoothly as possible. As a full-services electronic systems design firm, our professionals and engineers cover a multitude of service disciplines, including FPGA and ASIC design, embedded software, hardware, signal and power integrity, verification, and many more. We help our customers by supplying some of these expert skill sets directly or by managing the complete project from start to finish. And now I'm pleased to introduce our speaker today, Dawson Theroux, a seasoned embedded software designer here at FIDOS with deep expertise in implementing secure boot and trusted platform module integration in embedded systems. With years of experience working across various embedded platforms, Dawson has helped our customers enhance their security posture by protecting firmware and managing encryption keys during software upgrades. His extensive knowledge of TPM, secure boot processes, and real-world implementation makes him the perfect expert to guide us through today's session on securing software upgrades. So, without further ado, I'll hand it over to Dawson to kick off today's session. Over to you, Dawson.
Thanks, Alicia. Hi, everyone. I'm Dawson Theroux, an embedded software designer here at FIDOS Systems. This webinar will explore the importance, requirements, and implementation of secure software upgrade in embedded systems. Throughout the webinar, the security features and precautions of secure software upgrade mechanisms will be explored. This includes details regarding overall system security in embedded systems, the reasoning and implementation details behind secure software upgrade. Also covered is the use of TPMs to source secrets such as authentication and encryption keys used during the upgrade process, and common recovery mechanisms that can be implemented to recover a secure system after a failed upgrade. Let's get started by going over the common features of secure embedded systems. A secure embedded system consists of many components and configurations to offer system-wide security. Secure boot is the first component. It establishes the root of trust for the system by offering authentication, integrity, and encryption to bootloaders. For more information about secure boot, take a look at our previous webinar on the subject. Once secure boot establishes the root of trust for the bootloaders, the boot process is started, and the bootloaders must authenticate later components in the boot process to extend the root of trust. In addition to system boot security, it is important to lock down system access through system configuration. Some examples of this include burning system configuration efuses, such as the one to disable JTAG access. It is also common practice to disable the U-boot and UART console to limit access to the device consoles. Furthermore, for a system to be truly secure, it must be capable of adapting to new vulnerabilities, which can be accomplished with a secure software upgrade mechanism. Security is paramount in software upgrade mechanisms to ensure bad actors cannot exploit the system to their advantage. All of this is especially true in embedded systems that implement mission-critical applications, leading them to be highly sought-after targets. Software upgrade is a key component in secure embedded systems. Without the ability to upgrade a system, there's no way to fix vulnerabilities after a device has been deployed. Software upgrade is a sensitive process and can expose vulnerabilities since it interacts directly with the hardware responsible for firmware and software storage. If, for example, a problem occurs while writing the update to flash memory, such as power failure, then the flash memory write may fail, resulting in the device being unbootable. In addition to the sensitive nature of programming device firmware, software upgrade also exposes another attack vector that can be exploited by bad actors. In a secure system, implementing an unsecure software upgrade mechanism could allow attackers to utilize the mechanism to reintroduce system vulnerabilities that were intended to be blocked by securing the system. These vulnerabilities are mitigated by employing security and best practices in the software upgrade mechanisms to help minimize the attack vectors that software upgrade exposes. Let's go through some of the high-level characteristics of systems that implement a secure software upgrade mechanism. Boot process security is a foundation for platform security. In a previous webinar, we covered the mechanisms used by Secure Boot to establish the system root of trust by authenticating and encrypting bootloaders. Once Secure Boot has established the root of trust, it can be extended to components later in the boot process, again through authentication and encryption. Later, we will touch on how the root of trust can be used during secure software upgrade mechanism by including it inside of the root of trust. Trusting the firmware or software executed on the device is another key component to systems that allow for software upgrade. Boot firmware can be validated via measurements. These measurements can then be validated by the system to ensure that the software executed is as expected. Measuring software components is accomplished by hashing the memory containing the application that is about to be executed. Hashes are one-way functions that create unique fixed length values based off of variable input. The hashes generated act as a unique fingerprint or measurement of the software that is about to be executed. These measurements can then be sent to a remote attestation server that will be compared with expected measurements. The server will then indicate whether the measurements are valid or not. Attestation of the measurements can also be done locally with signed good measurements located on the device or using an external chip called the Trusted Platform Module. At a fundamental level, trusted platform modules can keep track of platform measurements using internal PCRs, or platform configuration registers. While keeping track of these measurements, policies can be created to store secrets against the values of these PCRs. This allows keys to be locked when the system is in an untrusted state, such as in Linux user space, or if the boot firmware has been modified, but be unlocked while the system is in an authorized state, such as in the early bootloaders. Common secrets stored in the TPM are RSA private keys and AES encryption keys, and are released only when the system is running specific software with specific PCR measurements. Furthermore, the TPM can be used to encrypt or decrypt data without exposing the AES keys in the same manner as an HSM. For example, during device manufacturing, the TPM can be programmed with a secret AES key used for decryption during the boot process. Then, when the TPM PCRs are in a specific state, then the TPM will be allowed to use that pre-programmed key to decrypt the data without ever exposing the secret AES key. Sealing secrets in the TPM against PCR values is only one method for storing keys provided by the TPM. Another common approach, especially in software upgrade, is to use what's called an authorized policy to seal secrets. With authorized policies, secrets are stored in the TPM with an accompanying public key. Access policies can then be generated and signed with the accompanying private key to define access conditions for unsealing the secret. This mechanism is extremely important for software upgrade, where PCR values change after a software upgrade. In this case, when the build server has generated the new firmware and software components the new PCR values can be calculated for those software components. The build server can then create a policy with the new values and sign it with a private RSA key. During the update process, the device can substitute the new policy for the old one. Then, during the next boot, new firmware will be booted, resulting in new PCR values. And since there is now a new policy that reflects those PCR values, the board will boot as usual. In turn, this process separates the TPM secret sealing process from the access policy creation, which is very convenient for software upgrade, where PCR measurements change frequently. Another aspect of securing the software upgrade process is being able to rely on the security implemented by the software upgrade application. Developing a robust application depends on the location of its implementation. One option is to implement the upgrade application in user space with very limited permissions. Although the solution leads to a simpler development and upgrade process, the upgrade application is vulnerable to operating system exploits. The Trusted Computing Group Guidance for Secure Upgrade of Software and Firmware recommends implementing the software update mechanism inside of a firmware upgrade latch. The firmware upgrade latch is a mechanism that prevents the software from being modified outside of the latch. One approach to implement a firmware upgrade latch is to include the firmware upgrade application inside of the root of trust as part of the boot process. This comes with the caveat that bootloaders are not always updated as part of the software upgrade mechanism, which means that a separate update application may be required to update the actual upgrade application. But this also means that the software upgrade application can be trusted since it's part of the root of trust. Software upgrade applications are a common attack vector used by bad actors to exploit systems since they have direct access to modify the firmware or software running on the device. One way that attackers may try to exploit the software upgrade application is through the upgrade package itself. For example, if the upgrade application does not provide authentication or integrity checks on the upgrade payload, attackers may be able to load their own software on the device. Even with authentication and integrity checks of the upgrade payload, attackers may also opt to leverage valid payloads to create vulnerabilities in the system. This is typically accomplished by attempting to upgrade the system with an older version of the software to reintroduce vulnerabilities that were previously patched. To solve this, software upgrade must ensure that the software being updated is a newer version than the one running on the device. Although encryption of the upgrade payload may not be required, it can be useful to implement to add one extra layer of security to the system. Since eliminating all vulnerabilities for a system is nearly impossible, encrypting the upgrade payload makes the upgrade mechanism more difficult to reverse engineer. In security, this strategy is called layered security, where you may not necessarily need encryption to protect the data, but it is useful to further obfuscate the process from bad actors. In a secure system, many of the mechanisms that could have been used for system recovery are inaccessible. As was explained at the start of the webinar, the U-boot console should be disabled, meaning that it cannot be used to reflash the firmware to the device in the case of a software upgrade failure. Many other common methods should also not be accessible for security reasons, like JTAG. It is for this reason that some sort of recovery system is necessary to be put in place to recover the system when the software upgrade mechanism fails, either from a bad payload or interruption due to power loss. Hardware watchdogs are used extensively for system recovery by catching hitches in the boot process and causing the system to reset during an unsuccessful boot. After a software upgrade, when a boot limit is reached, a recovery mechanism is usually initiated to recover the system from the non-functional state. Common strategies for system recovery include firmware recovery images and AB upgrade mechanisms. System recovery can be accomplished via a minimal firmware recovery image that boots after a failed software upgrade. This minimal image should allow for the delivery of an upgrade package and initiate the upgrade mechanism. With upgrade applications located in the boot firmware, the recovery application could be a boot component prior to the upgrade process. One reason to use minimal recovery applications over other options is the limited space used on the device. A downside, though, of firmware recovery applications is that they require a full new upgrade payload to be provided from an external source to be able to recover the system. The recovery image may also introduce new vulnerabilities, since it's a separate system from the upgrade application and the main firmware/software running on the device. Another strategy for system recovery is an AB upgrade mechanism. AB upgrade mechanisms store two full versions of the software on the device. The main flow works as follows. Say a system is booting with version A of the software and is prompted for a software upgrade. The device will take the upgrade payload and program it to version B of the software. Boot parameters will then be updated to indicate that version B should be booted and the system is in a software upgrade state. If version B of the software is booted and reaches a boot limit, which is a boot counter that increments every time the device is started, then the software upgrade will be indicated as a failure, and the device will seamlessly switch back to version A of the software. But if version B boots correctly, it indicates through the boot parameters that software upgrade is complete and version B is the official version of the system. An advantage of AB upgrade mechanisms is seamless system recovery by switching back to the previous version of the system. AB upgrade does require the device to be capable of storing two versions of all the software, essentially meaning that double the amount of storage space is required. Boot reversion logic is another vulnerable aspect of the system, since bad actors could revert to the unused version of the system to reintroduce system vulnerabilities. There's a trade-off between development time and the location of the AB version split. Typically, the AB version split happens in the second stage bootloader, such as U-boot, due to the available drivers. The downside of splitting in U-boot, though, is that all components before and including U-boot are not a part of the AB upgrade system. This doesn't mean that they cannot be upgraded, it just means that if upgrading these components fails, the system cannot be recovered. In some cases, it is possible to move the AB version split before even the first stage bootloader through creative use of multi-boot soft resets and bare metal applications, but the complexity of the system requires much more development effort. Frameworks exist for out-of-the-box software upgrade include Mender, Software Update, RAUC, and FWUP. The advantages of many of these applications is that they offer support for AB upgrades as well as over-the-air updates. For example, Mender provides U-boot drivers for AB upgrade versioning as well as over-the-air upgrades. These frameworks are not all open source though, which means that they may require licensing in commercial applications. This can be circumvented with a custom solution tailored to a specific requirement of the system, including TPM support or early AB version splitting. Encrypted file systems are a key component to secure systems protecting applications and customer data. Dencrypt with Lux partitions is a common solution for implementing this. Dencrypt sits between the read and write operations to perform encryption and decryption on the fly of the data held inside of Lux partitions. In addition to the file system encryption, it is also common to pair this functionality with a TPM to hold the secret used to unlock the file system. This ensures that the device firmware and software measured during boot are correct prior to releasing the key and allowing the file system to be mounted. If the secret used to decrypt and mount the file system is shared between the build server and the device prior to a software upgrade, this mechanism comes with the advantage that the software upgrade doesn't need to know the secret. Instead, the encrypted file system can be passed in its entirety to the device and used to overwrite the old partition. The downside of this approach, though, is that the upgrade package becomes quite large as the encrypted partition cannot be compressed very well due to high entropy. Let's go over an example of storing a secret in the TPM to be used by the system when it is in a trusted state. We will go over storing the secret in the TPM and demonstrate how altering PCR values makes a secret inaccessible. Currently on screen is a UART console connected to a KR260, an MPF SoC platform that includes a TPM. The FSBL has been patched to extend TPM PCR values with early boot component measurements. Using the TPM2 tools package in user space, I can interact with the TPM. Using the PCR read command, we can see the current state of the PCR values. PCR0 is extended with a measurement of the boot ROM. PCR1 is extended with a measurement of the first stage bootloader. PCR2 is a general PCR that's extended with many measurements, including the system device tree. PCR3 is extended with a measurement of U-boot, and PCR6 is extended with a measurement of the system bit stream. Next, let's go over sealing a secret in the TPM. In this case, we'll be storing the secret contained in secret.txt, which is hello software upgrade webinar. I've created scripts to help me during this webinar. One that creates policies, ones that seal secrets, and ones that unseal a secret. So let's go ahead and seal the secret in the TPM. So we can see it says it's sealing secret, and it gives the name, that the value of the secret it's sealing, which could be in reality an RSA or AES key, but in this case it's just text. And what it's doing is it's sealing the secret in the TPM using an authorized policy, which means that before this webinar I generated an RSA key pair, and it's providing the public key component and the secret to the TPM for storage. Next, we can create a policy to unseal the secret. The policy that's being generated is a PCR authorized policy, which means that it takes the current state of the PCR values and creates a policy. Then the policy is signed using the private key component of the RSA key pair. Now we can unseal the secret with this policy. Unseal secret. Policy 1. And we can see that the script prints the correct value. So what the TPM is doing in this case is it's taking in the new policy that we just created. It is checking the signature and making sure it matches the RSA public key that the secret is stored with. If that authentication passes, it will then check the policy value, which is in this current state is the values of PCR 0, 1, 2, 3, and 6. And if all of that passes, then it passes us back the secret. So let's simulate if someone modified a measured component of the system. So we'll do that just by extending a PCR with a random value. In reality, it could be someone changed the boot.bin, resulting in many different values being measured, but in this case, we can just change one. PCR extend 0 SHA-256. We'll extend it with a bunch of zeros, just in this case. Now, if we reread back the PCR values, we can see that PCR 0 has been modified and now starts with 2342, where originally it was with value 5E6A. So if we try and unseal a secret with our original policy, it will no longer work. You can see that it says policy check failed. This is because although the signature of the policy is valid, the PCR states that the policy was originally created with no longer match. Meaning that if somebody tampered with the system, then the secret can no longer be unsealed. In some cases, for example, during software upgrade, it makes sense that PCR values have been changed because maybe you have upgraded the first stage bootloader or any of the early boot components. Luckily, policies can be created on the build server since they know the measurements that will be extended to the PCR values, because these PCR values are all predictable. It's all just you hash the entire first stage bootloader, and then you provide the hash to the TPM, and the TPM will hash the hash of the first stage bootloader along with a bunch of zeros, the original PCR state, to get its new PCR value. Since hashes are a one-way operation and are irreversible, it's computationally infeasible to go from this value of 02342 back to the original value of the boot ROM measurement in this case. The only way to do that is by doing a reset of the TPM chip by toggling the reset line. In most cases, as is the case in this system, that's connected to the power on reset button of the device. So the only way I can go back and reset the PCR values to their original state of 0000, then extend it with the first stage bootloader hash, is by resetting the system and having the first stage bootloader re-extend those hashes. So in this case, after the system is reset, the original policy that I created will still be able to unseal a secret, since the TPM PCR values will be back in their original state. Log in. So we can see PCR 0 is back to 5E6A, the original value. And I can unseal the secret again with policy 1, since the PCR is back in the original state. And with that, I hope that demonstrates the usefulness of a TPM in a software upgrade system, a secure software upgrade system, as well as in storing secrets in boot components sort of later than secure boot. And with that, I would like to thank you all for listening to the presentation portion of the webinar. And I'm going to hand it back to Alicia.
Okay, thank you so much, Dawson. Here we are, and thrilled to watch these questions popping in. So just a quick reminder to everybody that if you have a question for Dawson, do pop it into the Q&A box at the bottom of your screen. So great presentation. Thank you, Dawson, for that. So we have a question here from Peter, which is, how do you manage two valid PCR states when implementing an A/B upgrade mechanism?
Yes, this is a very common scenario with TPM implementations and software upgrade, since you'll have your version A with one version of the boot firmware, which generates one set of PCR values, and then version B of the firmware that generates a different set of PCR values. So technically, they're both valid, secure PCR values that haven't been tampered with, but they will require different policies to open. So typically, this process is handled by the switching logic between version A and version B. So for example, if your U-boot image is what handles reading the boot parameters and deciding that version A is going to be booting, then U-boot will also typically read the policy that is used to unseal the secret from the TPM. So if it's booting version A, it will read version A of the policy, and if it's booting version B, it will read version B of the policy. So it will require managing more policies and secrets in the TPM, but it is definitely possible.
Excellent. Okay, Peter, hopefully that gets your question answered. Okay, this question is from Dan. If the ability to downgrade the system is a hard requirement, do you have a way to secure the software upgrade mechanism without implementing downgrade protection?
Not necessarily. Downgrade protection is a really key role in software upgrade, since the whole point is to patch vulnerabilities out of the system. If someone could just provide an old version, then that sort of nullifies the whole reason to have a secure software upgrade. So in the past, I've seen when you want to downgrade the system, you repackage that older version of the software as an upgrade, and then provide it to the upgrade mechanism as a newer version of the software. So in reality, it's your older version, but the upgrade mechanism sees it as an incremented software version, will allow it to pass and continue with the upgrade.
Okay, hang on, check. Next question here from Rusty. Hopefully I've said that name correctly. Are there any drawbacks to using an encrypted file system, like speed or increased chance of data loss? Anything else?
With encrypted file systems, there is a slight decrease in speed since you're doing that encryption process during your write operations. But in my experience, I haven't really noticed the file system become more sluggish. It's possible that if you're writing large amounts of data, like streaming from the FPGA or something, you might see a significant speed decrease. But in my experience, I haven't really seen any. Regarding data loss, you would think that having an encrypted file system would mean, in the case of power loss, it's possible that you sort of blow up your whole file system and can no longer like boot the device or anything. But in reality, it has the same journaling mechanisms as a regular file system. And the encryption is done on sort of like a small, like it's in small blocks of the entire file system. So like a regular system, if you unplug the power, of course, there's probably going to be a write error and then you lose some data. But in the case of an encrypted file system, the lost data is sort of at a block level versus maybe like a partially writing the data of a file. So you might lose a little bit more data, but it's not inherently a lot more risky than a regular file system. So it's worth the extra security that it adds for sure.
Okay, so I have a question here from Rolf. Is there an increase in required development time when adding a TPM to the device?
Yes, especially in early boot components. The drivers for U-boot especially are not fully fleshed out with all the features. When I've implemented authorized policies in U-boot, there is some amount of development that needs to happen to sort of implement that logic of providing the policy to the TPM with the specific command parameters and everything. But it's not a huge amount of development. If you don't want to sort of incur that extra development time, there is other alternatives such as Wolfboot, which is a security-focused version of U-boot, but it does require a license. I am pretty sure that Wolfboot does have a much more fleshed out driver for TPMs, but again, it's the trade-off of having extra development time and owning the changes to U-boot versus using somebody else's code like Wolfboot and paying a licensing fee. So without experience implementing a drive for TPM and U-boot, it might have some extra development time, but I think the benefits that having a TPM to store your secrets during a software in a software upgrade system is much more important than the extra development time that it might require.
Excellent. Okay. We've actually hit all of the questions now. So unless anybody has any other questions, I just want to give a bit of a shout out to the fact that FIDOS are going to be attending the first ever Embedded World in North America, coming up in October in Texas. So if anybody is on this webinar that's going to be attending, please do pop by and say hello to us. We'll be right near the Lattice, which is a partner of ours, right near the Lattice booth. And furthermore, Dawson already gave a plug, but we do have another webinar on a topic related to secure boot that is available on our website. We will be sending out the email recording to this webinar tomorrow once we've got it uploaded to our website, and I'll also include a link to that previous webinar. So last but not least, if there are any suggestions, if you have any topics that you'd like to see us cover, I do encourage you to write back to me and to give me that feedback. So Dawson, thanks again for your time today and for putting this together. Always appreciate seeing your face. And thank you everybody for joining us today. Talk to you soon.
Thank you.